So, hi everybody. So this is the continuation lecture of where we started last week. And the aim today is actually to build a neural network code. And on the way, while doing this, we will also discuss about some of the details, the mathematics of neural networks, their weak points, their strengths, and many, many other small details. So the idea today is more to be we are going to try to outline how we write a program for neural networks, and I will guide you through a Jupyter notebook where we do that. So this is a Jupyter notebook which is linked up with this lecture here. So it's the same, contains exactly the same material as the one you see in the slides here. I also wanted to remind you, so if you go back to the main GitHub site of the course which we have here on the Comp Science program, if you scroll down and look at the weekly schedules, you will obviously find the weekly lecture notes, and you will also find the video of the lectures. And if you click on the video here, you should also get a video with subtitles now. Okay, so let's go quickly back here to the topic for today. So the basic aim is to build our own feed-forward neural network and look at many of the gritty-nitty details which are needed if we want to set up a neural network. If you look into this textbook by Aurélien Géron, which you will also find under the textbook folder. So if you go back to the main website or the main GitHub site, if you click on doc here and you go to textbooks, which actually I did not put in here, but I'm going to put it in. So there's going to be a textbook folder where you can actually fetch the PDF file of Géron's book. So I'm going to put that one later. And then you have Goodfellow's text, in particular chapter 6 and 7 are very useful. So when we later move into convolutional neural networks, chapter 9 is extremely useful. Chapter 11 and 12 have lots of practicalities and applications on neural networks. And in addition, there is a textbook by Bishop, which is also pretty good on neural networks. Now, there are two videos here which can be useful if you want to look at them. In particular, the video on the back propagation algorithm is quite good. And this is the topic which I just wanted to remind you of before we move on to write our own neural network code. So we're going to quickly go back to the whiteboard and remind ourselves of some of the mathematical details when we look at neural networks. So one of the things which we computed last time, and I'm going to bring this up again when we look at the whiteboard, is a quantity which we call the output error. And this was the error which we had when we computed the derivatives of the cost function. And the derivative of the cost function contained a quantity which depended on the cost function itself, the output from the last hidden layer. And then it contained also an evaluation of the derivative of the so-called activation function, which becomes a kind of parameter. And then we did actually compute the so-called back propagation error, or we just back propagated the error till we reached the first hidden layer. And then we needed to compute a quantity which depends on the weights of a given layer, this activation function of a given layer, and also the error which we had from the previous layer. And with that, we could update the weights and the biases. And this is the basics of the back propagation algorithm, which leads to analytical or equations which we have to evaluate numerically anyway. It leads to a set of equations which define the gradients. And then the gradients are normally calculated by our favorite gradient descent algorithm. And one of the parameters, since we don't want to calculate second derivatives, or what we call the Hessian matrix, we replace that with a learning rate, which becomes a parameter. And this is one of the parameters which we normally fine-tune when we run calculations of neural networks. And we will see that in greater detail today when we are setting up our own neural network. So let me quickly remind you of some of the details which we have and which led to the backpropagation algorithm. So what I'm going to do is to switch back to the whiteboard before we actually start writing our own program. Anyway, feel free to ask questions if you have any questions while we move on. Use the chat if you prefer that, or just unmute yourself. So let's switch back to the whiteboard. So one of the things which we did last time was to define the quantities which make up a neural network. So we would typically have a hidden layer, and this hidden layer had a set of nodes. So let me just write it up very schematically here. So we would have a set of nodes, and each one of these nodes produced an output. So it received an input from a previous layer, and that would be an input which defined the input to the specific node. So we would have a hidden layer which we simply label an L, and this has a node which we would call Hi of L. Now this received an input, so the collection of all these quantities here defined an input to a specific layer, to a specific node, set I. Now this node produced then an output, and this output is something which we label for an AI of L. And this is something which we will propagate all the way till the final hidden layer. So we had reached then at the end here, after many, many such layers, we reached what we call the output layer. And this is something which we defined in terms of a variable. A given output from a specific node here is something which we label with an uppercase L. And this is the output of our network. And then depending on the type of problem we are looking at, whether this is a case which produces a binary output, then we would just need one hidden node. If we are producing a value or function depending on a set of input variables, then we would also just need one variable, and that will be compared with a specific target which we want to reproduce. So this is the quantity which we then would compare with the targets. To be compared with a target, and we label these targets with a T. So the typical thing then, if we are looking at a regression problem, a typical cost function could be the mean squared error, which we met in connection with project number 1. So that would be the mean squared error. And we would rewrite this one. If we now skip the division by the number of data, it would have a sum from I equal 1 up to n, total data which we have, of T of I minus A of I of n. So the thing we needed then, in order to define the parameters, was to take the derivative of this function with respect to the weights and the so-called biases. So each hidden layer and each node in the hidden layer receives also a so-called input, which is called a bias. So this would be a B of I. If this is a B of I, a specific node, let me just change this a little bit. So this specific node here would also receive an input from a parameter which we called the bias. So every node from the previous hidden layer is connected with every single node in the new hidden layer by the so-called weights. So here we would have a weight of a Ji coming from a node from a previous layer. There would be a Wli, a Wki, etc., etc. Now, the function which we defined then, the so-called activation function, is a function which now plays a very important role here, because that becomes a kind of parameter theory. So the input here produces an output for a function f set I of L, and that gives us an output AI of L. So the function which we have here this is a function which we call the activation function. And you can view that as a parameter. And there are several very popular activation functions. One of them is the sigmoid function, which we met last time. There's a tan hyperbolicus. There's something which are called the ReLU function, rectified linear units, and so on. So we are going to discuss them in a little bit more detail today. But there's one thing I wanted to mention to you about the mathematics of a neural network. So if you now think of a simple neural network where you have now 2 layers, simple NN, with total number of hidden layers, L equal to 2 here. So what happens then is that the activation function, which you would have in the final layer, so if we call this F, and we just write it F of X of theta. So X is now the input from the input layer. If we look at this function, this is now going to be given by a function which I'm going to call f of 2 here. And now I'm going to look at this as a simple neural network which has just one hidden node in each layer. So that means that there is a weight W2 here, and this is multiplied with a function f1, so which is the output from the first hidden layer. And this has now a function here which depends on an omega 1, and this is multiplied with the input, so there's just one input. So if we now look at this specific neural network, it has one input. It goes into a hidden layer, so this is the L equal to 1 hidden layer, and then we have L equal to 2, which we write with an uppercase L. So this feeds in here. There is a weight W1. This has also a bias B1. There is a weight W2 here, and there is a bias B2 here. And that produces an output, which is now given by this final function F. So the final output is now defined by the function which you see here. So I need to add some more details because this is now going to contain a plus B1. So that's the function which now produces the output from the first hidden node. And then there's going to be a plus a B2 here. So when we are calculating the cost function here, and we are updating the weights, and we want to optimize the weights, we need actually to take the derivatives of this specific activation function. So one quantity which we need then the derivative of this activation function, the final one. So you can think of this final F as the output from the network based on all the different activation functions which we have. And now we have simplified the network just to illustrate some of the mathematics of a neural network. So if I now take the derivative of this final quantity, x of theta, with respect to W1, which is one of the weights, and which we will need when we are calculating the gradients from the back propagation algorithm, this is nothing but sigma 2, no, sorry, not sigma 2, but f2 derivative. So we would have f2 derivative, and we would have omega 2 multiplied with f1, and then we have omega 1 times x plus b1 plus b2, and this is now multiplied. So this is just a multiplication sign. It's not the variable x, and this is multiplied with W2, and then I have the derivative of F1. So this is just a simple application of the chain rule, plus B1, and multiplied with the variable x. So I do, at the end here, I do actually have the variable x. Now, if I have now L layers, and L is different from 2, so let's now say with the L larger than 2 layers, what we end up with then is that this derivative is going to be equal to delta f of x, of theta, of w1. And this is now going to be given by the product. So I'm going to have a product here of L equal to up to the final layer of WL. And this is multiplied with, so I'm just putting a underscore here to indicate that this is my multiplication of a quantity. And then I have L equal to 1 here, and then up to L. And then I'm going to have the derivative of these functions of L with the input to these functions, set L. And this is multiplied with X. So this is going to be the derivative, one of the derivatives, which we need in order to set up the back propagation algorithm. Now, the problem which we face now is that if we look at the sigmoid function, for instance, so if f, this function f of L, is the sigmoid function, which is a very common choice in neural networks, what happens then, if we now take a look at the sigmoid function and make a sketch of it, and we take minus x here and x here, so x is the argument, and put minus was 0 here and plus 1 here. Now what we have is a function which becomes very flat when x becomes very large. So you see now the problem is that the derivative of f of L is very small, can become very small, is small when this x, which we would have as an argument, is much larger than 0. This leads to a unfortunate problem when we are training neural networks, which is called the vanishing gradients. So if we look back at the calculation of the gradients, we need the derivatives of this specific activation function, and that can easily lead, depending on the argument, to something which leads to a vanishing gradient. So when we are back propagating the different weights and biases in order to update them, what happens then is that we could actually stop the training because the gradients are equal to 0. And that may be an unwanted feature because we may not have reached the point where we have obtained an optimal cost function or optimized the cost function in the best possible way. So this is a notorious problem with neural networks, and that has led to the introduction of other types of activation functions. So that's why you should view these activation functions as a kind of parameters. So this led then to introduction of new activation functions, and you can view these as parameters. And when you train a neural network, what many people actually do is to train it with different types of architectures and also different types of activation functions. And there is a whole chain of such functions. And one of the most standard ones is something which is called the ReLU. So let's set up these functions. So we have a ReLU, which means a rectified linear unit. And this is a pretty simple function because it says that f of z is simply given by max of 0 and z. Now the problem here, however, is that for values of z larger than 0, set larger than 0, the gradient does not vanish, because then when we have z as a value, when you take the gradient, you just get a constant. So the gradient does not vanish. The problem, however, is if the argument is less than 0, then you may have a vanishing gradient. So one of the things which people have done then is actually to introduce something which is called the leaky ReLU. Now, one of the features which you see with these functions here is that you want all of them to have simple derivatives, because when you are setting up the backpropagation algorithm, what you actually end up with is a repeated set of calculations of derivatives. And obviously you want these calculations of derivatives to be fast and not very time consuming. And you would like to have an analytical expression for these gradients, which is simple to implement. So the functions which you see here, they are the kind of what you might call the result of trying to figure out which function could represent a kind of activation of the node. Like the sigmoid function is, if the value is larger than 0.5, you would say that it gives an output equal to 1, or it gives a specific output. If it's less than 0.5, it does not give anything. So the type of activation function will also depend on the type of problem which you have. So the leaky ReLU is now a function f of z, which is given by a parameter, which becomes a parameter we want to tune here, alpha times z for z less than 0. And typically this parameter alpha can be something like 0.01, so it's a small value, but it gives you a gradient which is different from 0. And when it's larger than 0, then it's simply equal to z. That's the so-called leaky ReLU. Then we have another function which is called the exponential linear unit, or the ELU, which is also very much used activation function. So that has an f of z, which is equal to a new variable alpha, which is normally something which you would tune. And this is multiplied with e to the power of z minus 1. And this is when z is less than 0, and then simply z when it's larger than 0. These are just some of the functions, and as you can see here, the derivatives, if you now take the derivative of this specific function, if I take the derivative of it, what I would get then is something which is pretty easy to implement numerically. So I would have an alpha times z of z when it's less than 0, and just 1 when it's larger than 0 or equal to 0. And similarly, when you take the derivative of the leaky ReLU, in that specific case, is just equal to this parameter alpha when it's smaller than 0, and it's just equal to 1 when it's larger than 0. So these are functions which give pretty easy equations for the derivatives. Now, another function which is very much used is the tanh. And in that specific case, we would simply have an f of z, which is equal to the tan hyperbolicus of z. And that has a derivative, which is also pretty easy to implement. So it's 1 minus tan h of z to the power of 2. In this case, the value z lives between minus 1 and 1. So these are the typical domains for the variables. And then the sigmoid is also one of these very much used functions. So let's put that one up for the sake of completeness. And the sigmoid function was actually the standard function because many people felt that that was a function which did mimic properly the properties of a neuron, a physical neuron. And you would think of this function as a function which would fire in case the signal was larger than 0.5. And it would not fire, it was less than 0.5. So the sigmoid function, when we put it up here, is equal to 1 divided by 1 plus e to minus z. And its derivative is also pretty simple. And that's simply equal to f of z multiplied with 1 minus f of z. So all these functions are functions which you can think of as parameters in your neural networks. Now, there's one more thing I wanted to say before we actually start building our own neural network, and that's about the universal approximation theorem. So I'm not going to prove it because that would take me quite some time, but I wanted to remind you of what it actually stands for. And this is one of the reasons why neural networks are that popular. So if you think of a classical approximation theory, one of the examples which we looked at in project 1 was to approximate the function with a polynomial. So in the classical approximation theory, if we look at that, what we typically have is a function which is going to approximate our data. And then we assume that this function is continuous on the unit circle. And then we can make statements like or we have theorems actually, like the Stone-Weierstrass theorem, which states that for each error which we fix, there exists a polynomial of a certain degree. So if we take the example of a polynomial here, so if we take the polynomial example, then what we have is a function x, which depends on some parameter theta. And we know that in principle, there is no upper bound on the polynomial. So we could have actually a polynomial of infinite degree. So we would have a sum over j. We would have this parameter theta j, like we did in the first project, and use linear regression. And then we would have a x of I here. And this is x of I, the specific variable, to the power of j. So in principle, there is no upper bound on the polynomial. So the Stone-Weierstrass theorem, and for those of you who are familiar with real analysis, you may have actually seen this proof before. So if we now assume that there is a function f, we assume there's a function f, which now is an element of on all the points on the unit circle in d dimensions, then there exists a parameter epsilon, which is so that for a given polynomial, we can actually approximate the function f of x here minus the true function, the polynomial which we have, theta, and we can actually make an approximation which is now smaller than a specific epsilon which we have defined. And this applies for all x values which live in the domain of 0.1 on the so-called unit circle here. So this epsilon is now a parameter, so we can actually fix a reproduction of the data which we want with a polynomial to a given precision. So this is an example of a typical classical approximation theorem where we have used a polynomial, and there's something called the Stone-Weierstrass theorem, which simply says that we can approximate this function with a polynomial to a given precision epsilon. You can do the same thing if you look at Fourier series. Then what you would find then is that you would have all the L-squared integrable functions, which then would allow you to approximate a function with a Fourier series. That's another example of it. If you go to neural networks, on the other hand, what the neural network says is that there exists, if you have one hidden layer, there exists an approximation to a function so that you can actually approximate this function to a given precision epsilon. So for neural networks, there's a theorem after Sybenko. What we have then, so this is actually Sybenko, which published this paper back in 1989. So you can have a sigmoid function, for instance, and this was later generalized to other types of activation functions. So let f, or let's change the notation a little bit here. Let sigma be any continuous sigmoidal function which has the property that this sigma of z goes over to a variable 1, and I have to actually to look up there's something I have written here. Yeah, so it goes to 1 when z goes to infinity, and it goes to 0 as z goes to minus infinity. And if we go up a little bit to what we had before, if we look at the figure here, the sigmoidal function is a function then, if we look at the plot here, you see now that when the argument goes to minus infinity, the function goes to 0. When the argument goes to plus infinity, then the function goes to plus 1. So that's the definition of a sigmoidal function. So with such a function here, so given a function f, which is now a complex function on a unit circle, d in d dimensions, and a parameter epsilon, which is larger than 0, then there is, and this is what the theorem says, so this is an exercise actually in real analysis, there is a one-layer neural network and we are going to call this neural network for a function given by a function little f, which depends on the input variables x. There is a set of weights, unknown parameters, and there's a set of biases, unknown parameters as well, so that these functions, or these neural networks, as we might call them, theta here, so of the form where these weights are now given by a matrix. And this is a matrix of dimensionality m times n. So you would have m input variables and n hidden nodes, and d, which is now a vector of dimension of length n. Then for these quantities here, for which what we will have then is that we would have an approximation. So this neural network approximates this specific function x, uppercase f, to a given position epsilon for all x, which are elements between 0 and 1 on the unit circle. So what we are saying now is that any continuous function, uppercase f, supported on the unit cube, can be approximated by a one-layer sigmoidal network to arbitrary accuracy. So this is normally called the universal approximation theorem. Now this was later refined by Hornig in 1991. We actually refined the theorem by letting any non-constant bounded activation function to be included. So we would not then be limited by only using the sigmoidal type of functions. Now, none of the proofs, however, give any insight about the relations between this accuracy and the number of hidden layers. So we have a need, at least the theorem states simply that with one hidden layer, you can approximate this function to a given epsilon, but it doesn't say anything about the number of hidden layers which are needed. It doesn't say anything about the number of nodes which are needed, and it doesn't say anything about the type of algorithms which we are going to need when we are going to, for instance, calculate the gradients. So universal approximation theorem simply states that we can approximate any continuous function with a neural network with at least one hidden layer. And Hornig actually improved the theorem by adding any non-constant bounded activation function. So that's the universal approximation theorem, which plays a very important role in the theory of deep learning. And it's one of the big motivations for why people typically tend to use neural networks in order to fit complex functions. So keep in mind, there are some additional subtleties here. If we look back at what we did in project number 1, then we fed into the design matrix a given model. And that model which we had was given by a polynomial of a certain degree. Now you can feed that type of design matrix into a neural network. What the neural network would do then would be to try to find the optimal parameters for a polynomial of a given order. So it means that you are forcing the network to produce a polynomial, the parameters of a polynomial of a given order. So suppose that your data actually are given by a 10th order polynomial, and you feed into a neural network an approximation given by a 5th order polynomial. Then the network is trying to reproduce the parameters of a 5th order polynomial in order to fit something which would actually have been a 10th order polynomial. So the philosophy of a neural network is actually that you let the network figure out what is the complexity of the function you want to reproduce. That means that the standard approach with a neural network is actually to plug in just the input values and let the network figure out what are the optimal parameters. Now, you could, however, let the network receive some kind of guideline. So in my case, where I'm using neural networks to solve quantum mechanical problems, I can give to the neural network some specific constraints, like the symmetry of the solution, whether the solution should be symmetric or anti-symmetric, because that can be difficult for a neural network to figure out. These are constraints which you would put based on your insights about the problem. However, if you don't know the degree of a polynomial and the data you want to reproduce are given by a polynomial to a certain degree, then you should let actually the network figure out what is the most optimal representation of that specific data set which you have. Any questions so far? So what I would like to do now is actually to go back to but not to the slides, but to the Jupyter notebook. And I wanted to discuss a little bit more in detail how we actually make such a network. And this is going to be the topic for the rest of the lecture today. So I wanted to bring up the Jupyter notebook, and we're going to look at all these small details in constructing the network. And I'm going to apply the theory we have developed now to a problem which consists of recognizing handwritten numbers. So let's now get started a little bit here. Any questions so far? So what we are going to do now is to set up first the backpropagation algorithm, and we're going to plug in all the gritty-nitty details of a neural network. So this is going to involve several parameters and functions. So we have to decide upon activation functions. We have to decide upon the architecture of the network, whether we want to have one hidden layer or many hidden layers, or many nodes we want to have in the hidden layer, what kind of activation functions we want to deal with, how we are going to calculate the gradients when we have the backpropagation algorithm. And in addition, we can also choose hyperparameters and so-called regularization parameters. And furthermore, we have to decide upon a learning rate. So a neural network becomes a kind of patchwork where we try to fit many different types of parameters and operate with different types of functions as well when we are looking at the activation functions. Ideally, what we would like to is to let the neural network figure out which are the activation functions as well. That leads into the very interesting topic of Bayesian neural networks, where you actually end up replacing these simpler functions with probability distributions, which are defined by the Bayesian neural network. And that's a very, very active field of research. The drawback with that kind of approach is that it becomes numerically very, very expensive, because to evaluate a probability distribution is very time consuming compared with these simple activation functions, which we are going to look at now. So there's always a trade-off here when you're looking at the setup of a neural network, and you have to strike a kind of balance between the accuracy of your result and the number of CPU cycles which you are allowed to expend or which you're willing to expend. So let us now look at the way we are going to set up the neural network. And I'm going to guide you through the basic ingredients here. So the first thing, we need to set up the input data. We need to define the activation functions. And the example which we are going to go through here is an example with just one hidden layer. And we need to perform the feed forward step till we reach the output layer. So we will then have this output. So when you see the bold-faced quantities, these are just vectors. If you're feeding in the, let's say, a multidimensional input to a function, like the Franke function we had, where we would feed in x and y, we would just have one output for one given value of x and y. So if you have a multidimensional function in many, many dimensions, you would then typically have, suppose you're dealing with a 10-dimensional problem, you could have 10 input values, and they may conspire to produce just one output value. If you're looking at these handwritten numbers, we are going to look at categories. So we need to classify properly the handwritten numbers which we feed in. And these handwritten numbers, since we are dealing with numbers from 0 to 9, we are going to have 10 numbers, which means 10 categories of outputs. If we have just a binary case, we can just have two outputs. It could be 0 and 1. So these are the types of outputs which we need to consider, and they will obviously vary from case to case. So the output error is something which we need to compute, and then we're going to back propagate that one back till we reach the last hidden layer. And these are the equations we need to set up. So when we now are going to look at the problem, we are now going to specialize to this MNIST data case, which is a classification problem. And if you go back to what we did in logistic regression, we defined a function which we call for the cross entropy. And this is going to define the cost function, to which we are going to use to compute derivatives of in order to find the optimal parameters. So the cross entropy, if we are looking at a binary problem, a typical two-class problem, is the optimal function. If we are dealing with more than two categories, two classes, then we will typically use something which is called the softmax function, and which is a generalization of the standard sigmoid function. So let's just move down. So if we now look at the typical sigmoid function, if we're now looking at just two classes, we would now have a probability which represents the output from that function, which is now given by the standard sigmoid function, which we have met many times. And then we would then have the output 1. So it's a binary problem. So if we take 0, then 1 is obviously 1 minus the probability of getting 0. And y takes simply values 0 and 1, and theta represents the weights and the biases of a network. When we then define the cost function, what we did in logistic regression, if we go back to these logistic regression lectures, then we would simply use that one, the same function, and this y of i's are now our targets. The p of y's here are what the model produces. So when I produce an output in the final layer, that is going to be the quantity which is produced by this function p. And then y is going to be the target which we want to reproduce. So if we just scroll down a little bit, if we also have a multi-class problem, then it's common to actually change each variable into a so-called one-hot vector, which is actually a binary bit string. So you can see now, if you want to classify the number 5, you will transform that one into a bit string. And in this specific case, you would just need 10 bits. And you see now that this one, the one here, will just correspond. If you translate this one into a decimal number, that will simply correspond to the number 5. So that is one way by which you could represent the numbers. If you have a binary class, life is very easy, because then you will just have ones and zeros. That simplifies really life. So if you're dealing with a probability of this x being in a class C, you will typically end up using the softmax function, which we are coming back to. And we encounter that one when we discuss neural networks. So what you see down here is just a set of repetitions of what it would look like when we deal either with a binary classification problem or a multi-class classification problem. So for project number 2, we may actually think of looking at either a binary classification problem or a multi-class classification problem. So if we have a binary class problem, if you go back to logistic regression, what we had then was a cost function which depended on the parameters beta. And in that specific case, we would simply have the probability which was given by the logistic function. And then we had the parameters beta 0 and beta 1, which we would determine by a standard Newton-Raphson algorithm or just a standard gradient descent algorithm. And the functions will be given by this, and we could use something like a gradient descent method. But now we're going to replace these x's with activation functions or the activation inputs, and then the outputs are going to be given by the inputs given manipulated by the activation functions. And this is what we're going to get. And if we now look at the final layer, the output layer will now have an uppercase L here. And in the case of a binary problem, we will simply be evaluating a function like this. So I'm going to stop now. We take a small break because I see that I'm a little bit above the hour. So the aim of this lecture is to go through the basic elements of the construction of a neural network. So before the break, we looked at some of the mathematics of neural networks, and we started discussing one of the typical applications, which would be a classification problem. And if we do a classification problem, we would encounter cases like a binary classification problem, where we just have 2 types of classes, or we could have a so-called multi-class classification problem. And in that case, we would end up using a function which is called a softmax function. Now, to quickly remind you of some of the quantities which we need to evaluate, one of them is the cost function for the final, at the final layer. So that's where we produce the output from the network. So the network is our model. In the same way as when we did linear regression, we would have an input to the design matrix in terms of a polynomial of a specific degree. That would specify our model. Now, the neural network is our model. And the ingredients of the model would then be the number of hidden layers, the number of nodes we are dealing with. We would also have types of functions, regularization parameters. We would have activation parameters, and so on and so on. So the targets which you see here represented by T, these are the quantities which we want to reproduce. The log of the probability, which is represented by, for instance, the output of a sigmoid function, is now in this specific case, the output from the last hidden layer. And this is marked with uppercase L. And this is the quantity which we would compute the derivative of. And one of the ingredients which we need when we are setting up the backpropagation algorithm is the derivative of the cost function with respect to the weights. And when we do that, we get something which is now dependent on the type of activation function which we have. So in this specific case, we have used the logistic function. And then in case we are using something like the ReLU function, or we are using the leaky ReLU or exponential ReLU or the tan hyperbolicus, then we would need to replace the denominator here with another derivative. So the quantity which you see here in the denominator, that can be traced back to the derivative of the specific cost function which we have opted for. No, sorry, not the cost function, but activation function. So you could now replace what you see here with the derivative of the cost function multiplied with the derivative of the cost function with respect to the parameter AI at the final layer, multiplied with the derivative of the specific activation function. So when you're writing the program, what you would need to do then would be to, for instance, set up derivatives of different types of activation functions, and then you could play around with these activation functions. So one of the quantities you need is then obviously, as we said, the derivative of the activation function. So the quantity which you see here, this df with respect to z, is something which will vary from function to function. So when you write a neural network code in an object-oriented fashion, clearly what you would do then would simply be to set in a specific class of activation functions and their pertinent derivatives. So if we take the softmax function, which is now given by this function here, and in our case, this would only be applied to the last layer, because that's the output layer when we have different classes. So we have more than two classes. And then it's pretty common to use a softmax function. So the derivative of that function is just listed here. So it looks pretty much like the one you would have from the logistic function, except that we have a Kronecker delta here. So if you have a binary model, this simply reduces to 1. So when we now are developing a neural network code with a backpropagation algorithm, there are 6 essential steps which we have to bake into the construction of a network. So we obviously have to collect our data. We have to decide how we want to set up the input data. And we will see with these examples of handwritten numbers, which are given by images, which we want to classify properly, that there we would have to feed in the pixels of an image. That would be the input data. Then we need to define model and architecture. We need to choose the type of cost function we want to use. And in the classification problem, it's typically the cross entropy, which we'll be using. We need to figure out what kind of stochastic gradient function we want to use. So that's the optimizer. Then we obviously have to train a model by a repeated feed forward and back propagation stages. Then we have to evaluate the model and test on the test data. And then finally, we may need to adjust hyperparameters if we are dealing with a given type of regularization term, which we add to the cost function. And clearly, it may also be needed to modify the network architecture. So all these things are basic gritty nitty ingredients which we need to set up in a neural network here. So if we now look at the setup of the data, let's look in more detail at this MNIST data set. In principle, this MNIST data set has 70,000 images, and the images are actually not very good. So they're just 28 times 28 pixels, so it's not a very high resolution. And each such image is labeled from 0 to 9. So the data set is a fully labeled data set. The data set which we are going to look at is a downscaled version of this 28 times 28 pixels, it's actually downscaled to 8 times 8. So in total, we have something roughly around 1,800 images. So when we are setting up the design matrix, what we are going to have then are the number of inputs, which will be close to 1,800. Or if we do a split into training and test, then clearly we will have less than 1,800. And then we need to set up the features as well. So each row represents an input. In this case, it's a handwritten digit. And each column would then represent a feature, in this case, a given pixel. And then the correct answers, also known as labels or targets, are then represented as a one-dimensional array of integers. So numbers like 5, 3, blah, blah, and so on. So to give you a simple example, suppose you want to have a neural network which finds out based on input data of weights and heights of persons. You could find what is the body mass index. So the typical input matrix, or the so-called design matrix, would then be a matrix which contains, in this specific case, we have 5 people, so there are 5 rows, and each feature is now given by the height in meters and the weight in kilograms. And then the targets would be the body mass indices, which you have calculated based on these. And then you want the neural network to actually find, based on the trained model, you want the neural network to be able, when you now feed in the weight and the height of a person, you wanted to find the body mass index. Now, in our case, the situation is a little bit more complicated because we have every image is a 2-dimensional matrix. And what we do then is actually we flatten the image. So if we go back to Python, this is the same as using the ravel function when you take a 2-dimensional matrix into a 1-dimensional array. So you may remember this Python functionality, which is called ravel. And that gives you allows you to transform a 2-dimensional matrix into 1-dimensional array. So what we do here is simply to read in the data. And I'm using Scikit-learn, which has a series of data sets, which are then tuned to these kind of calculations. So this is the reduced MNIST data set, which contains 1,800 data points. And if you now look at the data sets, you load the data sets. So we have the inputs, which are the images, and then we have the labels here, which are defined by the targets. So this is already set up for us. We don't need to do any thinking concerning the inputs. And then what I'm doing now is simply to find out the length of the inputs. So I have the number of inputs, and then I'm setting up the arrays, and then I'm just printing out here. So what you see now is that I have 1,797 inputs, and I have 64 pictures. So the 64 pictures are the pixels. So the original input is now 1,797, 8 pixels times 8 pixels. And then I flatten this out to 64 pixels. Now, the thing is that when you look at these images, they have already been labeled correctly, but the pictures are very blurred. And the reason why we have such a low dimensional picture is actually because this allows us to run the calculations rather quickly. So the design matrix has this dimensionality, 1,797 times 64. Then, as usual, we split the data into train and test. And a pretty common splitting is 80% for training and 20% for testing. So, and then we would basically use the train test split functionality, which you have with Scikit-learn. And this is what is done here. So the train size is 80%. And then there is an example here where you could actually write your own program. So feel free to do that. I have just run through this. So this contains now 1,437 training data and 360 test images. Then what we need now is to define the input layer and the output layer and the hidden layer. And then we have to decide upon an activation function. So let's see how we do that now. So we are going to look at the sigmoid function as the function for the hidden layer, and I'm going to use the softmax function for the output layer. So let's look at this. So we're going to set up an input layer, which now takes for every image, it has 64 inputs. So which are the pixels, or we may just call them features. Then I have my hidden layer, and in this specific model, I'm going to have 50 nodes, or neurons, as we call them, or also call them. This means that since this is a fully connected system, it means that since I have 64 inputs and 50 hidden nodes, I get 3,200 weights which need to be trained in order to find their values. In addition, I would have 50 biases, which I also need to train in order to find the right values. So 3,200 plus 50, so 3,250 parameters for the hidden layer and its connection with the input layer. Now, the hidden layer is connected with the output layer. And if we were to use a binary classifier, we would just need one single neuron, because that single neuron could just output 0 or 1. And we could use something like the Heaviside function, or we could actually have used the sigmoid function for that specific case. For soft binary classifier, like the one we have now, we have 10 classes, which are the 10 handwritten numbers. So we would then have 10 categories, and that means that we would end up with 10 neurons in the output layer. And we would just number these from j equals 0 up to 9, which are the numbers. And these would now be given, the outputs which we would get would be given by the softmax function. So the weights and the biases, which I would have in this specific case, since I have 50 hidden nodes, which connect with 10 nodes in the output layer, I have 500 new weights. In addition, I have 10 biases for the output layer. So I have 510 new parameters which I need to train, in addition to the 3,250, which came from the connection between the input layer and the output layer. So this is actually a baby case when we are looking at the training of neural networks. So the standard neural networks contains millions of parameters which need to be trained. That leads to a extremely high dimensional problem, which may not reach a convergence at all. It depends on the number of cycles we are willing to spend, the type of problem which we have. The function may not be a convex function at all. The training may be very difficult. We may get stuck. The weights, the training of the weights may die out because we may have vanishing gradients. So it's setting up a neural network is very much a trial and error experimentation, where you try different activation functions, you try different structures in order to see if you're able to produce an output which is reasonable when compared with the targets you want to reproduce. So when you're setting up the weights and the biases, then they are normally initialized with small values, which are distributed around 0. And it's pretty common to use a Gaussian distribution, a normal distribution with a 0 mean value and a variance which is equal to 1, for instance. That's a pretty common way to initialize the weights and the biases. And then what you would typically do then, so let's look at the code here, because that's often the best way to see it. So we now define the number of inputs and the number of features. We set up the number of hidden neurons to be equal to 50. So we have only one hidden layer. We set up the categories we want to deal with, which are 10. And now what we are doing is to set up the hidden weights. In this case, we would now have a matrix of weights, which is given by the number of features times the number of hidden neurons. So in case of one specific number which comes in, we would have 64 times 50. And then we have the biases, which we simply now initialize to a small number. So you could have opted for a random number according to the normal distribution if you wanted to, but you can also just fix that to a small number because this is going to be trained anyway. And you would normally set the bias to a non-zero number in case the weights end up being close to zero. Because if you don't have this hidden bias, which is different from zero, the network may actually stop even in the feed-forward stage. And then finally, we do the same thing. We initialize the weights and the biases for the output layer in the same way. So except that then the dimensionality is smaller. So the first stage we do now is a feed-forward pass. So we run through the network by a feed-forward pass. So we define the number of features, the number of hidden neurons, and the number of categories. And then we compute the different activation functions. We calculate the inputs to the final output layer. And then by that, we have now the outputs, which we compare to the targets in the cross entropy in this specific case. So I'm going to skip some of the details here because some of the details are things which you can look up, but you can see now the complexity of the problem and the mathematical operations which you end up doing. So remember now that all the nodes, input nodes, hidden nodes, and output nodes, they are all fully connected, which means that we have dense matrices, and we end up having matrix and matrix vector multiplications as the basic, and I should say time-consuming mathematical operations. So these are typical operations which you also would like to parallelize and make more efficient. In essence, what we end up with is an input to a given node, which is given by a matrix times a matrix, or matrix times a vector, plus a vector here, which is now the bias vector. And this is passed into the activation function, and this is finally fed into the output layer. And in our case, the output is given by the output from the softmax function. So let's look at the details of the feed-forward pass. So there's no back propagation here yet. So we define the sigmoid function. This is the activation function for the hidden node and the hidden layer. So we define now the inputs to the activation function, set H for hidden. And this is a matrix multiplication between the feature matrix and the hidden weights, which we have initialized, plus the hidden bias. And then we calculate the activation for the hidden layer. Then we repeat this because that feeds in to the output layer. And then we have the softmax output, which is just given by the sum of probabilities. So I get this input set output. I feed that one into the exponential terms, and then I simply compute the softmax function here. And that is the probability which I return. And now if I print these probabilities, I can then make my prediction. And if I look at that one, so this one specific number which I'm looking at is a prediction for a specific image, which I predict to be 8. And the correct label is actually 6. So I didn't do too well. What we need to do now is to define the cost function. We need to decide on how we want to treat the targets, how they should be encoded. And the typical thing you would do when you have a multi-class problem is that you would treat each integer as a bit string. And in this specific case, you would just need 10 bits to classify the 10 integers, of which represent handwritten numbers. And if we just go down a little bit, we need also to plug in a new parameter, which is the learning rate, which controls how big a step we take towards the minimum. And in the update of the weights and the biases, this becomes a very important parameter. And we use the backpropagation algorithm to find the expressions for the gradients. So we need to also include this gradient descent method. And the typical approach is a stochastic gradient descent, which is very common. And that is what is implemented in the code below here. So these are things which we have discussed before when we go back to our lectures on gradient descent approaches. So I'm not going to repeat that. You can, in addition, add a regularization term, and it's pretty common to have typically an L2 norm. And in the calculations which we have below here, we have actually added a regularization term on the weights, not on the biases. And these are the regularization terms which we will typically end up with. And that means that the cost function which we would evaluate at the very end, which means when we now have the output from the output layer, then we would compare this with the targets, and we would simply take the derivative of this function here. And this is where the regularization term enters. So that's an additional term. So as I said, for this simple case here, we have 3,250 weights from the input layer to the hidden layer, and 510 weights to the output layer, plus the biases, obviously. And we have to calculate the gradient for each of these parameters. And we use the backpropagation algorithm, which we derived last week. So, which is just a clever use of the chain rule that allows us to calculate the gradients efficiently. So the backpropagation doesn't calculate the gradients, it just gives the expression for the gradients. So we end up with a series of matrix vector multiplications and matrix-matrix multiplication, as we have been discussing. And let's now look at the code here. So here I'm implementing the coding of the images in terms of bit strings. So this is done in this part. Then I'm doing the feed forward part. And in the feed forward part, this is just a repeat of what we saw above. So I'm calculating my output from a feed forward pass. And then I have my back propagation here. So I'm setting up the derivatives of the cost function. So if you go back to the function which we had in the very beginning of these slides, you will find the derivative of the cross entropy. This is one part of the function which we need. Then I'm calculating the error in the hidden layers. So I'm setting up the correct expressions according to the backpropagation algorithm. Then I calculate the gradients for the output layers, and I calculate the gradients for the weights and the biases using the expressions which I have. And I do the same for the hidden layer. And then this just returns the weights or the gradients and then the bias and of the hidden weights and the hidden biases as well. Now, what I need to do then is also to plug in my parameter for the learning rate and the regularization parameter. And in this specific case, what I'm doing now is simply to call this back propagation. I add the regularization terms, which is this lambda term here, times the output of the weights and the hidden weights. I update the weights and the biases. So this is my back propagation here, but I'm just running, I'm not doing a stochastic gradient descent, but I'm simply just setting up the gradients here. And if you look at the training accuracy, which I have, this is not very impressive. So what I'm doing now is I'm simply counting the number of correctly classified images divided by the total number of images which I have in my training data. And you see that this is not very impressive. So I haven't baked in a stochastic gradient descent, and I haven't run over more than just one learning rate and one parameter lambda. So what we are going to do now is actually to improve the performance, and we are going to run over several hyperparameters. So we're going to take learning rates from 10 to the minus 6 to 10 to the minus 1. And we're also going to choose this regularization parameters from 10 to the minus 6 to 0, or not to 1. And then we are going to do a stochastic gradient descent. So my fully object-oriented code now is just written in terms of this class, which I call for neural network. So it takes the number of hidden neurons, the categories. It's going to set up a stochastic gradient descent. It has 10 epochs, 100 batch sizes. It starts with a value for the learning rate and for the regularization parameter, but these can be changed according to the specific learning rates and regularization parameters, which I fixed. And what you will see here is just a repeat of what we did. So we create the biases and weights. We have the feed-forward stage, the feed-forward output. So this would be the feed-forward hidden layer, which you have here. You can now, if you look at the structure here, you can add more hidden layers to this. This is our output layer. And in our output layer, we have explicitly coded the softmax function. This is something you can make more flexible by adding other types of outputs. If you're dealing with a regression problem, it's common not to have any activation functions. You just simply give as output what the neural network, the final hidden node, would the node in the output layer actually produces without any activation functions. So this is in case of dealing with a regression problem. Then you have the back propagation, which is set up here. And then you make your predictions. And then you have the training part. And in this specific case, you're using the stochastic gradient descent. The way you test whether you have done well or not is to compute the so-called accuracy score, which in this case is just the sum over correctly classified images divided by the total number of images. So if this y tilde of I, which is our result, agrees with the result we want to reproduce, then it's 1. If not, it's equal to 0. So we're now running over number of epochs. We do a batch size. I can actually increase the number of epochs as I want. I can play around with different types of parameters here. I do my neural network here. I train, and then I have my prediction. So this is very much the same way as you would set it up if you're using Scikit-learn or TensorFlow. Then I calculate the score, which is my accuracy score, and this is set up here. And you see now that when I've done this training, I get a pretty decent result, which says that the accuracy score on the test set is 0.94. What we normally do then is to perform a grid search in order to find the optimal hyperparameters for the network. And in this specific case, we're just using one layer with 50 neurons. And keep in mind that the human performance on these numbers, which you see, is roughly 98%. The numbers are pretty blurred. I'm setting up an array of learning rate values. So this is a parameter which go from 10 to the minus 5 to 10 to the first. And I do the same with the lambda values. I initialize my neural network, and then I perform a grid search now, where I simply run over these hyperparameters, the learning rate and the regularization parameters. And then I run my neural network, and then I simply write out the prediction I make as a function of the learning rate and the lambda parameters. So if you run this Jupyter notebooks, you will now see different values coming out here. You could have replaced this one with a grid search. So functions like Scikit-learn actually perform a grid search in order to find the optimal parameters. Alternatively, you can do the way as I'm doing here now, and simply running it, the code for the different hyperparameters. Now, it's very convenient to actually make a plot here. And you will now find that the software like Seaborn, if you're familiar with that, allows you to visualize all these results in a much better way. So let's use Seaborn. So Seaborn gives you a very nice heat map, and it allows you to visualize the results in a much better way than just this plain brute force printout. So if I look at the code now, if I rerun it, so I'm just rerunning over all the values of eta, the learning rates, and the regularization parameter. I train my network, and then I also calculate the accuracy score for the training case and the accuracy score for the test case. And then I'm going to plot them in terms of a heat map. And this looks actually a little bit nicer, as you can see here. So on the y-axis here, I have the learning rate. And on the x-axis, I have the regularization parameter lambda. So the first value here is 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, and 10 to the minus 2. And you see now that for 10 to the minus 2 and 10 to the minus 3, I'm getting a training accuracy, which is pretty good. So here, for 10 to the minus 2, I'm getting a training accuracy, which is close to 100% correct classifications. And I have a hyperparameter lambda, which goes from 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 1, then 10 to the power of 0, and then 10 to the power of 1. And you see again that there is a whole chain of regularization parameters where I'm getting a pretty good result for the training rate. And then if I look at the test rate or test accuracy, you will now see that I'm getting a test accuracy which is close to 96%, which is not bad for this neural network, which is almost handmade. I haven't done any optimization of number of epochs, number of batches. So these are parameters which you can keep tuning. Now, when you tune a neural network, one of the parameters which is most sensitive to the, one of the parameters to which the accuracy is most sensitive to is actually the learning rate. So one of the things you would do then, when you have tuned the learning rate and found which learning rates are the most important ones, you can then minimize the number of learning rates to just 1 or 2. And when you have that, you can play around with different types of architectures. So it's pretty common to run a grid search where you find the optimal learning rates and the optimal regularization parameter. And when you've done that, then you can start tuning the other parameters. So you would have parameters of the architecture of the network, which would be the number of hidden layers and the number of nodes you have. You would you can try to change the activation functions and see if they give better results. You would change perhaps the gradient descent method. So like in the application we had here, we had a plain stochastic gradient descent with a given number of batches and a given number of epochs. But you could change that one, this plain stochastic gradient descent, with an adaptive one. You could use Adam, you could use RMS prop, or some of the other methods which often are which normally give better results. So you have many different types of parameters and functionalities which you can try out. But the first thing, since these are the results to which the network is most sensitive to, is to tune the hyperparameter, like this lambda parameter, and the learning rate in the gradient descent method. So when you've done that, then you can tune the other parameters as well. And this is something you will do back and forth a little bit till you find a model determined by the number of layers, the number of hidden nodes, the type of activation functions, and the type of gradient descent method, which gives the best reproduction of your data. So one thing I wanted to show you before we take a break for this week is actually to discuss a little bit about the way you can implement this with Scikit-learn or with TensorFlow. So Scikit-learn as a library has a lot of functionality. However, it doesn't have a well-advanced functionality on deep learning methods. So what it provides is a multi-layer perceptron, or as we've been calling them, feed-forward neural network. And this is given by two options. So one for regression, so that is an MLP classifier or an MLP regressor. So these are the two functions which you would call when you want to set up a neural network. And this gives you essentially a feed-forward neural network where you can specify how many layers you want to have, what are the hyperparameters, what are the activation functions, and so forth. So if you prefer to use that, you can now see that if we now go and look at the MLP classifier, what you would need to do then if you look at the way you call Scikit-learn here, you would define the classifier which you want to implement. In terms of this, you would import this MLP classifier. You have to set up an array for the learning rates and for the hyperparameters. And then the MLP classifier now needs as input the number of hidden layers. It needs as input the activation functions. It needs as input the learning rates, the hyperparameter lambda, the regularization parameter. And you also need to specify the number of epochs. There are more parameters, and I normally advise you actually to take a look at the input variables to the MLP classifier. So in this case, we are running the same type of calculation which our own handmade neural network has been doing. So when you run this with the Scikit-learn, you will actually get a slightly better accuracy. And if you look at the plots which you have when you use Seaborn, you will see now that there is a larger region here where you train correctly all the training data with 100%. And if you apply this to the test data which you actually have cases here with 99% accuracy, which is actually better than a human classification of the same data. So on average, humans on this 8 × 8 pixels data, they would classify correctly 98% of the data, whereas our neural network has been trained now to classify 99% of the data, which is actually pretty good. And that is on the test data, which we're not included in the training. So in general, this code here, which is provided to us by Scikit-learn, has some further calculations, in particular with the gradient descent method, which are slightly better than the ones which I have implemented. But the basic philosophy is the one which you see in our own setup here. The reason why I emphasize this is that you should know what the input parameters actually mean. That's the most important thing. So you can actually play around with different architectures for the network. So Scikit-learn has a feed-forward neural network, but the functionality of Scikit-learn is actually not that advanced. Next week, I thought we could discuss in more detail how to use TensorFlow. And we're also going to look at some other examples of applications of neural networks. And one of the cases we're going to look at are some test cases which are widely used in order to demonstrate the feasibility of neural networks. And these are some famous gates. One of these is the so-called XOR gate, the OR gate, and the AND gate. And these are gates which have been used to demonstrate the universal approximation theorem, that if you have at least one hidden layer, you can actually reproduce data from an XOR gate, which you cannot do if you don't have a hidden layer. So we are coming back to that next week. And then we're also going to look at how to implement TensorFlow. And at the end of next week, we're going to wrap up the discussion about the feed-forward neural networks. And when we are done with that, we will start applying them to other systems. And in particular, we're going to look at how to solve differential equations. But next week, we will discuss further implementations and applications of neural networks. We are going to see how we can do this with TensorFlow. And most likely, we will then start applying neural network to the solution of differential equations, because I know that many of you may be interested in that as a possible variant of project number 2. So one thing I wanted to have you to start to think about is what kind of topics would you like to study in project number 2? So one default topic after we've done with the lecture next week is to implement neural networks in the studies of differential equations and perhaps eigenvalue problems. But the there are many, many other topics which we can study, because after next week, we are going to look at convolutional neural networks and classification of images, which may be of interest for many of you who deal with classification problems. So please feel free to forward topics for data which you want to analyze in project number 2. As I said, the default one is going to be studies of solutions of differential equations, and these are also partial ordinary differential equations and partial differential equations with neural networks. So I'm going to stop the recording now,